Okay, recording started. So hello everyone. Welcome to today's Origin seminar. Today we have our second talk from the NASA's Alien Earth team in this semester. Our speaker for today is Tim Lichtenberg. Tim received his PhD from ETH Zurich in 2018, and he is currently a Simons Collaboration on the Origins of Life postdoc research fellow in the Department of Atmospheric, Oceanic, and Planetary Physics at the University of Oxford. We'll hear him talking about molten exoplanets. Without further ado, let's welcome Tim.
Yeah, hi everyone. Thank you so much for this very nice introduction, and thank you for giving me the chance to present the research of me and my collaborators here. So let me share my slides. I presume it works again. So so I basically work on the geophysical evolution of rocky planets, specifically forming planets in their outgassing atmospheres. Sort of an intersection between geoscience and astronomy. I'm aware that usually, so this is more I feel from the talks that are usually presented here at the Origin seminar, many of them are related or presented from an astronomical perspective in a way. And I will do that too, but the motivation why I'm doing this is maybe a little bit different. Specifically, that while we continue to explore the exoplanet census, there's always the notion that we find something about the habitability of these worlds and potentially life in the universe. But I believe that actually at least during the active working time of most of the people here in the audience, we can find out something more profound actually about ourselves, about our own planet rather than other planets, by studying exoplanets and by studying their physics and their chemistry. So that is actually united by that question. So one of the central research questions that I tackle is, what kind of world was the prebiotic Earth? Basically, what is the type of planetary environment that gives rise to prebiotic chemistry ultimately, or promotes a specific pathway to prebiotic chemistry? And that seems awfully Earth-centric in the beginning, but I believe it is not, and we can study this question actually by looking outward into other systems and understand their diversity. So before I continue with this, the two background images actually illustrate part of the uncertainty that we have on this question. So from an astronomical perspective, we may think, well, we're standing right on the Earth. And so why don't we just study Earth if we want to know something about its evolution? And the reason is that 4.5 billion years of geological activity have basically erased nearly all telltale signs of the earliest Earth, the earliest 500 to 1,000 million years that were very likely let's say, the breeding ground of prebiotic chemistry. Perhaps not the first 500 million years, but certainly the first billion or 1.5 billion years of evolution. And the uncertainty is so large still that both the left-hand side image, which shows very hellish conditions with frequent meteoritic bombardments and massive volcanic outpourings, and the right-hand side of the image, which shows a clement sun, a nice ocean, hydrothermal systems, both are very much within the range of uncertainty that we understand at present day about this time frame. Now, of course, since 20 to 30 years, we have increasing diversity in planets. And compared to before 1995 or so, we really start to learn much more about planets in general, right? So from a very general point of view, to put this in as grand words as possible, we can start to explore general principles of planetary physics and chemistry, having many, many samples and not just one. Now, in these corners here, like studying actually the Earth and studying exoplanets, relies on multiple things, multiple aspects that usually are studied in isolation, but when considering the evolution and also the formation of planets, from a planet-centric point of view, not from a planetary system point of view. I'd like to distinguish this when talking about specifically the geophysics of planets. So I show them here in these three corners, ones that I want to highlight specifically. One is the stellar environment here on the top right. This plot specifically shows actually how the ultraviolet flux at the surface of rocky planets depends very strongly on the star that specific planet is circling. And that is particularly important for the prebiotic environment of planets, because certain theories for the origin of life very sensitively depend on the type of ultraviolet flux at the surface. And of course, because it's not only a matter of not only the irradiation environment is important for that in that context, but how it is processed on the planet. And for that, the atmosphere is primarily important, because it sort of attenuates the irradiation that is received from the star. And because secondary long-lived atmospheres, specifically in rocky planets, which is what I focus on, are connected to the interior through volcanic emissions. So the atmospheres, long-lived atmospheres on rocky planets are established by volcanic outgassing. So interior processes that are shown on the top left side here, like core formations, so structure formation, silicate melting processes, and things like this, are directly connected to the atmosphere. And so this kind of closes the loop, also between the interior and stellar radiation environment, but it's even more so connected for rocky exoplanets. For instance, atmosphere-less rocky exoplanets that we currently at present time have the capabilities to characterize, even more so, of course, with JWST from the end of the year on. Now, this already starts sounding like a standard astronomical exoplanet talk to some extent, but I want to shortly circle back here. What is the connection with the origins of life? The origins of life is really the abiotic processes that drive rocky planets, because ultimately these set certain geochemical behaviors of the surface. And the origin of life is essentially a redox-driven chemistry. And so what this plot here shows you is for various important nitrogen and carbon compounds, it shows you the important feedstock molecules that are needed to form essential biomolecules. One important one specifically here is hydrogen cyanide. So cyanide-driven chemistry is very favored in many specifically sub-aerial scenarios for the origin of life. And you can see here that, for instance, for nitrogen compounds, -3 oxidation state is favored, while for carbon, actually, more neutral oxidation state is favored. And we can understand these processes in these environments by constraining the planetary physics and chemistry in certain evolutionary eons. And that is what I do. Now, I want to zoom in into this plot here from the top left, which basically shows you an evolutionary wheel of rocky planets from the formation stage, the planetesimal stage, and the protoplanetary disk, which lasts on the order of 10⁶ years, that goes over through the giant impact phase with an approximate time scale of 10⁷ year, and ends with the crystallization, solidification of the planetary mantle, and then goes over into a billion-year-long phase of secular geodynamic evolution, at least for Earth-like planets that are beyond certain critical irradiation limits. And I don't want to go through all these processes, but I'm of course happy to answer any questions about these. What I want to highlight here specifically is most of their diagrams actually red. And that is supposed to indicate that the mantle is molten. It's not solid like we experience every day on Earth today, but the mantle itself is a liquid. And that is extremely important in the context of the planetary evolution, because liquid-gas interactions facilitate rapid chemical exchange between subreservoirs. For instance, between the core and the mantle, and at the same time between the mantle, the liquid mantle, and the atmosphere. And that means that much of the current structure and chemical reservoirs have very likely been established at the time of the magma ocean, or one of the magma ocean episodes, for instance, that happened on Earth, and very likely also happened on other planets due to various reasons. So this is particularly interesting in terms of exoplanets. This again connects the Earth with exoplanets, because gives us opportunity actually to study temperature pressure regimes that we do not have access to at present day. Temperature pressure regimes and chemical regimes that are extremely important for understanding what makes habitable planets or what breaks them. So in this plot here, you see temperature and pressure. Here's the approximate range of NTP that we can probe today on Earth. And in other colors are different regimes shown of exoplanets that actually probe a variety of processes. And if we want to understand the planetary context of the origins of life on Earth, we need to understand actually this regime, approximate regime, which we cannot probe on Earth today. And it's very hard to reach this also with even the most sophisticated, let's say, laboratory experiments. So exoplanets offer a natural laboratory to probe these regimes and extend our understanding in, let's say, accessible parameter space that we have access to at present day in the solar system. In terms of regime diagrams, specifically talking about atmospheric formation, the climate regimes we can expect for exoplanets, this is shown on the left-hand side here. This is a qualitative regime diagram, so without numbers, because it's very sensitively dependent on the specific composition and other factors that are not shown here. So where the x-axis shows the instellation, so going to the left here where the star would be here, this is planetary mass, and in different colors, you see different expected regimes based on our understanding of atmospheric physics, composition of planets. And in red dots are shown some known planets from the solar system and some specific exoplanets of interest. Now, the exoplanet detection sequence is from the top left to the bottom right because of the sensitivities of transit and radial velocity surveys. And that gives us immediately the opportunity to study the hottest and the hottest exoplanets that basically probe this high temperature regime. So we're coming from the top left, and what you can see here is that we first probe this blue diagram, which illustrates that in this diagram, maybe for Earth, potentially Earth-like planets, like planets that are rocky in nature, potentially in the mass regime of the Earth or a bit above, these may be the primary atmospheric constituents. So what is interesting here is that in this stage, many of these exoplanets, at least a certain part of their evolutionary transitions, experience magma ocean phases by irradiation. And to illustrate to you the fundamental importance of that transition, I show you here this plot from Hamano 2013, which basically is an illustration of the inner edge of what we usually call the habitable zone. But this is not an end-stage transition like what is usually discussed when we think about the liquid water habitable zone concept, but it is a primordial transition. That is even more fundamental than the habitable zone transition, the runaway greenhouse at the end stage of planetary evolution, because it may deny planets becoming habitable in the first place. So this is a complicated diagram, so let me walk you through it. So this is orbital distance in astronomical unit. This is final water inventory in Earth oceans. This is the solidification time in years. Different colors indicate different initial water inventories that are inherited from planetary formation. And what you see is basically for an evolutionary model of magma ocean evolution for considering only water, how, depending on the evolution at a given orbital distance for a given water inventory, how much water is retained during that evolution of the magma ocean. And what you see is that outside of a certain critical distance, the planets that are agreed to become water rich, let's say they start with 10 Earth oceans or something like that, they retain that water. So they basically are able to cool down. Their water, the steam in the atmosphere initially condenses out and forms water oceans. On the other hand, planets inside a certain critical distance actually don't. They, according to this diagram here, they lose most of their water content and end up dry and desiccated, potentially explaining the difference between Venus and Earth today. And why is that? The reason is that in the steam atmosphere stage, basically when the whole of the planet or a large portion of the mantle is actually in liquid magma form, the irradiation that is received from the central star, in this case for an Earth-mass planet and around the G star, so basically the solar system perspective, the irradiation is higher than the amount of energy that can be re-radiated through the atmosphere, because water vapor is a very strong greenhouse gas, and therefore at a given above a certain temperature, the amount of energy that can be radiated to space is fixed. And so the only way these types of planets can cool is via photolysis in the upper atmosphere and H loss. And this is what may have potentially what may potentially have happened in Venus' deep past, and is immediately applicable to many exoplanets that we observe, specifically for M-star exoplanets, because these have an extended pre-main sequence star that's very luminous. And so basically all M-star planets that we can observe undergo exactly this evolutionary, have undergone exactly this evolutionary history. And so we must understand and unravel these processes and how they operate in the very potentially very complicated compositional phase space that we see for exoplanets. Because that is so, we must study this in the full, as I said, potential phase space of composition that these planets may harbor. So you see differences in their behavior already when plotting certain greenhouse gases alone, a certain likely atmospheric species in isolation. So this is shown here. So this is for basically for a different surface temperature in Kelvin from 3000 to 200 K. So the crystallization sequence would be going from left to the right. This is the heat flux that is expected for atmospheres of 260 bar surface equivalent pressure. And you see that different major atmospheric gases have very different heat flux properties. And that is because they have different greenhouse effects, essentially because they have different rotational properties. Now, for the two most interesting cases, so here you see what I talked about earlier, the H2O runaway greenhouse limit, the so-called tropospheric radiation limit. And for the two most interesting cases that we typically discuss in the community, the H2O and H2 case, you'll see on the right-hand side here a model that resolves the magma ocean, the crystallization of an Earth-like magma ocean at 1 AU in this case, to start with the simplest possible case, resolved from the core mantle boundary, which is here at the bottom, to the top of the atmosphere. So this is height in atmosphere in kilometers, this is depth in mantle. The solid lines are the beginning of magma ocean crystallization, the dashed lines are the end, or not the end, they are after 1 mega year of evolution. And you see that these, depending on the composition of the different initial composition of these magma oceans, the scale heights of these atmosphere differ substantially. Very simplistically, because of a different mean molecular weight atmosphere. But in general, this suggests that depending on composition, we can distinguish them. For instance, via the transit depth. This is obviously used in transmission spectroscopy for understanding the composition of exoplanet atmospheres. And we can do so in principle also for magma ocean planets, be it close range, short period exoplanets, or ultimately planets at wider orbital separations. This becomes more complicated, of course, when considering the full flurry of potential solutions, different species. So this is a very degenerate problem, but we must act on this, because this is really what defines the climate state of rocky planets during the subsequent billion years of evolution, or at least it gives us a handle on the initial composition of atmospheres after the emerge from planetary formation. So to show you that this is not just theory, we have exactly this discussion currently in the exoplanet community, where for GJ1132b, it has been claimed that there should be, several groups have claimed that they think they see an H2-rich atmosphere, which was immediately rebuked or criticized by other groups. While for K218b, for instance, there have been multiple groups showing that actually this is likely a sub-Neptune which has a water-rich water component, which is probably very water-rich. So in this discussion, these two end-member cases, the hydrogen-rich and the water-rich atmospheres that we potentially expect for short-period exoplanets as well, are basically the end-member states that we can expect for planets as a result of the coupled interaction of the interior and the atmosphere. And here comes the redox state into play, the redox state of the planet in general. On a planetary scale, oversimplifying things now, the redox state is basically the electronegativity of the constituent atoms of the mantle. Because secondary atmospheres outgas from the interior, the constituent atoms, specifically the major elements, define the composition of the gases that are outgas. So this is shown here on the bottom plot. So this is the electronegativity according to the Pauling scale. This is the atomic mass. And these here are the most cosmochemically abundant elements, where those elements here on the top typically escape to space. That's just by gravity. And those here at the bottom typically segregate to the core. So they contribute to the iron that makes up the cores of planets. So if your planetary mantle is basically more composed of elements that are to the left here of this diagram, then your composition is reducing and more prone to H2 rich atmosphere. While if it is on the right, it's more oxidizing, more prone to H2O. To quantify this a little bit more, this is shown here on the right-hand side plot. What you see is the x-axis. In this case, this is the redox state given to a petrological buffer that is often used in petrology and geochemistry. In this specific case, this is the so-called iron wustite buffer, which is defined as the equilibrium reaction of iron with oxygen making FeO wustite. And the y-axis, the volatile mixing ratio, and log units of the mixing ratio of a specific species. So what you can see, if you are here, let's say 4 orders of magnitude below the iron wustite buffer, then these atmospheres tend to become very H2 rich. So volcanoes on such worlds would outgas H2, while on Earth, for instance, volcanoes dominantly outgas H2O and CO2. And so the interior, the composition, and the processes that contribute to its evolution directly determine the composition of the atmosphere, of long-lived atmospheres of rocky planets. Now, are there certain theoretical expectations for these types of worlds? Are there certain dominant physical processes that define, let's say, trends that we can test with current or future exoplanet observations? Yes, they are. One of these processes is that from geochemistry and from studies of the solar system planets, we would expect, I call this here a main sequence of planetary atmospheric composition depending on planet size, where in this main sequence, reduced atmospheres would be expected for smaller planets. So first of all, everything normalized to the same elemental composition. If you would assume that all the planets accrete to the same composition and only differ in size, this is the effect that I'm showing here. Yeah. So if we have small planets, then these should tend to form reduced atmospheres, while larger planets should tend to form oxidized atmospheres. You may ask, why is that the case if you just said they all accrete to the same composition? That is because certain geochemical reactions in the interior overprint the compositional assembly that is inherited from formation. One of the major mechanisms that may contribute to this is, for instance, a mechanism called iron disproportionation, where, like shown here, a compound with Fe2+ forms to react another compound with Fe3+, so a higher oxidation state, and Fe0, called iron metal. This is illustrated here. And this iron metal is denser than the ambient mantle, specifically if we are in the magma ocean phase. It would sink to the core, but that net oxidizes the planetary mantle. So you basically remove here on the bottom left, you remove this iron from the mantle, and this drives the overall composition of the mantle to the right. On Earth, for instance, this happened via reaction of wustite with aluminum oxide, forming perovskite, the dominant mineral of Earth's upper mantle, and iron 0, Fe0. In latest papers, in general in planetary literature, these two reactions that are shown here on the left-hand side are the ones that you read most about. This one specifically for the solar system, studies of the Earth, for instance. And this one here has gained some traction recently in the exoplanet literature with regards to formation of water by the reaction of wustite with hydrogen forming water and iron Fe0. Now, those mechanisms are potentially very powerful and can overprint the composition of the mantle. And just realized, I'm sorry, I should have said this earlier. So this main sequence is operating actually because the geochemical reactions, for instance, iron disproportionation, are strongly pressure sensitive. They only work above a certain pressure range. That means if your planet is small, the pressures are not sufficient to actually so that these reactions can operate, they don't happen, and the atmospheres that are outgassed basically approximate the composition that is inherited from accretion in the first place. While on larger planets, actually these reactions can go forward and overprint the primitive assemblage. Okay, now that we have this out of the way, in addition to the increased pressure, they require mixing. They require mixing between the atmosphere and the mantle and the core to operate, because this iron 0 here needs to segregate to the core, and at the same time then the mantle needs to outgas to the atmosphere to re-equilibrate the mantle composition and the atmospheric composition. What I want to do now here is to convince you that this very simplistic qualitative prediction from geochemistry for larger planets may be broken at a certain mass range. In order to illustrate this in the first place, I want to show you this movie here, which is a fluid dynamic simulation of the magma ocean on Earth, so the terrestrial magma ocean. The metal core, imagine the metal core to sit here at the bottom. The atmosphere is here at the top, and what is simulated is just the mantle column in a rectangular box. So there's a temperature difference between the metal core and the atmosphere that drives convection. And that basically drives the eddies and currents that you will see. And what you see here are these black particles, and they stand for, in this specific case, they stand for silicate crystals, but they could also well be in a different regime. They could, for instance, be iron particles that have a density difference relative to the ambient mantle. And when I play this movie, what you see is these large-scale eddies operating that are driven by the temperature difference between metal core and atmosphere. But what you also see is actually that these particles do not rain out like you would expect them to. And that is because the kinetic energy in the flow and the friction of the liquid magma with the iron droplets suspends these particles. It can suspend them depending on the fluid dynamical regime of the magma ocean. Now, this is a computational experiment which very strongly under-resolves the Rayleigh number, and that is because we cannot actually achieve appropriate Rayleigh numbers at present day with computer experiments, nor can we do that in laboratory experiments. In general, though, we can understand the behavior by looking at the Rayleigh number, which is a measure of the turbulent strength or the convection regime of a convecting system. Above a certain Rayleigh number, usually 1,000, materials basically start to convect. Magma oceans are mostly in a regime of 10 to the 20, 10 to the 25, depending strongly on the specifics of the composition of the magma ocean and the column depth. And this is what I want to show you here. The Rayleigh number depends on the cubic power of the magma ocean depth, on the length scale of the convecting system. And that is important if we look at the difference, for instance, between Moon, the Earth, or a super Earth, or a sub-Neptune. Now, from laboratory experiments, we have a rough understanding of the scaling behavior, for instance, of the expected iron droplet sizes that we should expect in such a flow. And we have an approximate idea for the size threshold, assuming, of course, that the scaling theories that are developed from these convection tank experiments actually hold to planetary sizes. And so this is what I've done, I think, in the middle of last year, trying to understand the settling behavior of iron droplets is suspended in the magma oceans of sub-Neptunes or super Earth. And what you see here is the magma ocean depth in kilometer, iron droplet diameter in centimeter. The different line styles are different planetary heat flows that depend on the on the specifics of the primary atmosphere, for instance, on the composition of the atmosphere of sub-Neptunes, which is generally hard to know in general, but it also is, of course, an evolutionary quantity. Now, what you see in blue are the expected sizes. So the sizes, the droplet sizes for iron droplets, for instance, that are formed by geochemical reactions. And in red, we see the sizes that are entrained. Now, let's focus actually on this middle part here, which is for planetary heat flow of 10 to the 5 watts per square meter. Left of this point, gravity wins, and iron droplets would rain out, segregate to the core, and geochemical reactions would net oxidize planetary mantles. While on the right-hand side, on the other hand, rainout would be quenched, and actually the entrainment, suspension, the flow would win over the expected sizes. And this suggests that, contrary to what we expect from the solar system, on a planetary scale, net oxidation of planetary mantles may be suspended above a certain size regime. It depends on other quantities, not only on the mantle column, but for instance on the irradiation. But in general, if with continued exploration of the oxidation state, for instance, of surfaces, or the composition of potential secondary atmospheres in super-Earth, we may see diversity there, which may partly be allocated to this mechanism that I outline here, where Earth-like planets up to a certain size would self-oxidize by these geochemical reactions, while larger planets, specifically in the sub-Neptune regime, actually, they may show hysteresis behavior that ultimately reflects the compositional assemblage to which they accreted in the first place. Now, this is not only of interest generally for planetary evolution, but directly circles back to what I started with, namely the origins of life. Because in such age-dominated atmospheres, actually, we may find evidence for feedstock molecules of prebiotic chemistry. This has been shown a few months ago. If a mechanism like this is operating in the interiors of during the sub-Neptune to super-Earth conversion, this is a mock observation, so a synthetic transmission spectrum showing transit radius as a function of wavelength for JW. Just in general, this is a synthetic spectrum. Here is the window that can be observed with JWST NearCam. And you see that specifically, for instance, features of cyanide-acetylene are observable in these atmospheres. This plot here is for GJ1132b, which spawned the controversy that I talked to you earlier about. Now, in the last minutes, I want to shortly zoom out a little bit from single planets actually to planetary populations. And this therefore shows you a diagram of masses of planets, of known exoplanets with their uncertainties as a function of their scale density relative to the Earth. So the Earth is over here at 1, and you see the 3 regimes of sub-Neptunes, super-Earth, and super-Mercuries, a few, I think, increasing numbers of very, very high density planets that we know by now. Now, the general explanation for this trend is that the planets on the left have more water or gas, for instance, H2, while the right planets are composed of denser materials. For instance, they could have larger cores. And this would be easy to say, and with these shell models that you see on top, if they would neatly separate into distinct classes. But you see they don't, right? There's actually a continuum of planets in density space. And that suggests that, sorry, my mouse stops working. Yeah, better. I'm sorry for that. So this in general suggests that more complex mechanisms may be operating. For instance, actually, this very simplistic picture of multiple shells surrounding a planet may be broken by mixed components, or we may want to consider different thermodynamical states, such as magma oceans. And why we want to do this is illustrated actually by the color of the dots. While yellow shows planets that are so hot that even without any greenhouse effect, they would be molten because their surface temperatures would be above 1,500 K, or in many cases even above 2,000 K. But for the red dots, and this is literally nearly almost all of them, a substantial atmosphere of a few tens of bars or even less would be sufficient to actually turn these planets or bring them into the runaway greenhouse effect, bring them into a runaway state, where their surface temperature is enhanced by the greenhouse effect to such an extent that their surface temperature would be above the melting point of basalt. And in order to probe the effects of this, in a recent paper where we explored basically the potential impact of this on our understanding of volatile budgets of planets, specifically the water content. For that, we compared 3 different scenarios: a dry solid interior model. This is a mass radius model, where this is the most commonly used one in the literature, where the core is solid, the mantle is solid, and the atmospheric layer can be composed of all the 3 phases, so solid, gas, or liquid. And we compared this with more advanced models, a dry melt solid interior model and a wet melt solid interior model, where the dry melt solid interior model allows, so let's call it model B here in red. This allows the core to be molten and the mantle to be molten, but still all the water is put into the atmosphere like it is done in model A. And in model C, actually, we also accounted for the effect of water partitioning, because water has a high partition factor. So water likes to be in melt. So there's a system where there's water interacting with a steam layer, then actually most of that water goes into the magma and chemically binds or is partitioned into this magma, not contributing actually to the atmospheric layer. This means that the atmospheric reservoir decreases relative to this party. So quantitatively comparing this, what would be the impact of these 3 scenarios? This shows here water mass fraction and weight. This is the radius deviation between model C and model B, where C is the wet melt solid interior model and B is this dry melt solid interior. The difference between these scenarios is up to 16% for very standard water mass fractions, while comparing model A with model C, it is still up to 8% in radius difference. And so this is very hypothetical at this point, but let's turn this question around. What if we observe a specific planet, and we only know its mass and radius? Telling from the transient radius, let's walk up here a line. Let's focus, for instance, on this one here, 0.8 Earth mass planet. The difference for a fixed radius that we observe from an exoplanet survey, for instance, can be up to one order of magnitude in inferred water mass fraction, because there's a model-dependent degeneracy between these 3 scenarios, where these scenarios here are the smallest that feature the most water in comparison, for instance, A or B. What does it mean for specific planets? For specific planets, this means that some of them can harbor much more water than we thought, but others actually can harbor less if you use this thermodynamically self-consistent model. I want to here specifically highlight actually 55 Cancri. And contrary to previous studies, actually, we find that 55 Cancri, just based on the mass, its mass and radius alone, so its density essentially, it can host several weight% of water if the mantle is partially molten, with a 0.01% steam atmosphere on the surface. And this is interesting in terms of planetary evolution, because it suggests actually that previous escape models of planet populations, but also for specific planets such as 55 Cancri, have overestimated the amount of atmospheric loss that may be operating. And that is because all of these models put all the available gas in the atmosphere, while in reality, it would actually sit in the planetary mantle and maybe locked up in the mantle and not be able to contribute to the outflow. This means that we require new models that are coupled, where the escape is coupled to the interior evolution of the planet. And I think I have roughly 3 more minutes left. I want to shortly highlight one last issue here, which is the tectonic regime of rocky planets, how it is connected to climate diversity of super-Earth. So the left-hand side picture is the phase curve from LHS 3844b from Kreitberg 2019, which shows no evidence for a hotspot shift and therefore suggests there's no substantial atmosphere that can basically reallocate heat, shift the hotspot essentially. LHS is here, an interesting part of the diagram. And we used basically the input from the inference from Rydberg 2019 last year to model the potential tectonic evolution of that planet. So what you see here is the cut through of the planet. This is the star facing side, so the substellar point. This is the antistellar point. This is the metal core. And the flow field here is the solid state convection in a 2D simulation of the geodynamics of that planet. Importantly here, this is for a weak lithosphere, meaning a yield stress of 10 megapascal. And this means that the rocks at the surface of that planet are assumed to be rather weak, which, for instance, may suggest wet accretion outside of the snow line. And in this particular case, the geodynamic simulations that we have done suggest that the day side should be dominated by upwellings, so it should be hot, while the night side should be dominated by downwellings of the rocky material. And this is an intuitive regime that you would expect like this. But interestingly, if we vary the yield stress, or the strength of the rocks of the upper mantle of this planet, which we have no access to, then the opposite happens. And downwellings actually are focused on the day side, while the night side shows upwellings. And this scenario would actually correspond to something that is probably was undergoing dry accretion, so no substantial water component that made it into the mantle at some point. And this suggests that multiple things, actually. So first of all, this hemispheric dichotomous regime has been suggested for multiple solar system bodies so far, but it very strongly suggests for the temperature deviation that we expect for this planet in case there's no atmosphere present or a minor atmosphere present, then this planet is not actually in a stagnant lit regime, rather it is in a hemispheric tectonic regime. If you're interested in this, we have also plots for the surface mobility, which shows that none of the regimes we actually find to be realistic in accordance with the phase map is the stagnant lit planets. Also, this suggests that actually the volcanic emission, if we can potentially trace this with the scheduled JWST observation, the JWST program for that planet, gives us a hint actually for the volatile accretion history to the planet, which is linked to the tectonic regime of the planet. Right, and because I'm running out of time and I want to leave some minutes for discussion, I want to shortly just highlight the work that we've been doing in order to connect the climate regimes to the geodynamics of these planets, specifically a high temperature transition that is relevant for understanding Hadean-like climates, first on exoplanets and then make inferences on the early Earth. So we've been developing this model that I show you on the right. So on the left you see the physical setting for the magma ocean model, and I showed you some plots from this earlier. Which couples basically a thermal model of the core to multiple physical and chemical mechanisms in the mantle, to multiple physical and chemical mechanisms in the atmosphere. And this is not one code, but it's a code framework where multiple modules speak to each other that resolve the radiation transport, thermal photochemistry in the atmosphere, and the interior dynamics and interior chemistry. And to just highlight two aspects of this model, it basically makes possible a direct connection between the melting state and the 1D resolved melting state of the mantle with the atmospheric composition. And this is shown in this plot here, where this is a synthetic spectrum. So this shows spectral flux density as a function of wavelength. Blue is a water-dominated magma ocean. Green is an H2-dominated magma ocean. And the different line styles show different geophysical properties. We have, in general, a very, very poor knowledge of magma ocean solidification. And in this case here, we vary different potential scenarios for magma ocean evolution. Case one is a fiducial case, basically what everyone else does, a bottom-up crystallization scenario where directly the magma ocean interacts with the atmosphere, so liquid phase boundary to the atmosphere. Case two varies the mixing length, which in this specific case is made dependent on the distance to the nearest boundary. In case three actually introduces a boundary skin, which we see on lava lakes on Earth, for instance, and which may have operated in the magma ocean regime as well, and which introduces a thin boundary crust that very strongly inhibits thermal cooling through this crust. And what you see is that the spectra for these different assumptions strongly differ by several orders of magnitude, because in the interior, the mantle melt fraction varies at a specific stage of evolution strongly. And that means that connecting these 1D resolved models with long-term climate evolution will give us at some point a quantitative handle actually on the different potential evolutionary regimes in the magma ocean phase and how this translate to different climate regimes on rocky exoplanets. And I just want to very shortly say one sentence on that paper, which was led by R.J. Graham, a DPhil student at Oxford, who derived a new solution to the temperature pressure structure of arbitrary multi-component atmospheres with arbitrary ratio of condensable species. And so if you work in that area where you do simulations of multi-component, potentially complex atmospheric compositions, I'd be happy if you would give this paper a look. Maybe this equation will become useful for you, and I think some people in the audience are trying. Have already found this may be useful. Okay, and to finish this, to finish in time. So very shortly summarizing what I said, basically the atmospheric composition is directly connected to the interior composition in redox state. So we must study the trend, not only planetary formation, but specifically the transition then from the end state of planetary accretion to what this makes planets do in the long run. And we only can understand this by incorporating the geophysical and geochemical evolution of rocky planets. The redox main sequence that we expect from the solar system may be broken due to an inefficient core mantle segregation in a rain-out quenched regime, and that suggests that we should expect reduced secondary atmospheric composition surface mineralogy in a subset of super-Earth. The thermodynamic states makes a first-order difference in volatile budget by locking a large amount of water in partially molten exoplanets into the interiors. And this suggests that we need to reevaluate previous atmospheric loss calculations. And last but not least, atmosphere-stripped super-Earths are likely in a hemispherically split tectonic regime, where the day versus night side volcanic emissions is a potential tracer for their volatile history. In order to connect this now to the origins of life on Earth, what we need to do in the upcoming years with the increased surveys of exoplanets is explore the formation processes of planetary atmospheres and the compositional range of the interiors, which, and sorry, this is cut off, with that establish actually the ratio of reduced versus oxidized planetary climates that can give us some insights on the transition of this regime during the Hadean eon on Earth. Thank you very much for your attention.
Thank you, team, and you are well in time. So please raise your hand if you have any questions. So we have a question from Neil. So do you want to ask yourself, or I can read it out?
Sure. So in the you showed some hemispheric tectonics modeling, but so I didn't hear the word rotation. Could you say just a little bit about how rotation might impact the picture that you showed and how stellar tides might impact it? In other words, for example, if you're around if you have the same temperature, but you're around a lower mass star and therefore closer and therefore more likely to be tidally locked, does it change things?
So we assume the planet is tidally locked. This is basically why there's such a strong temperature deviation, because these planets can be expected to be mostly tidally locked, and therefore the hotspot or the temperature deviation between day side and night side is permanent to some extent. There may be mechanisms that reorient this, but we haven't taken those into account. With regards to heating, we tested for different internal heating regimes, for instance, radioactive heating or different types of secular cooling. And these are included, and this is basically included in my conclusions about this. We haven't modeled impacts. yeah, I don't know about impacts. I think so. This is the long-term evolution. This is a billion-year-long evolutionary regime in a sense, and so I agree that impacts would change that depending on the size of the impact, or they may induce permanent states. But we haven't tested this either so far. So this is something what would need to be doing.
Thanks.
We have a question from Daniel.
Yes. Hi, Tim. Excellent talk. I enjoyed it. It's, I'm still digesting some of the details, but I found it great. I had one question on. I had a question on the impacts too, but you mentioned that. I was wondering about the argument with the iron droplet sizes. If I understand right, you are basically taking those to be constant, as set by the flow. But I was wondering whether would you expect those droplets to actually eventually merge, or are they distributed so sparsely that the chance that they actually meet is?
Yeah, I believe you. I believe your question comes from may come from. This is essentially the same calculation you do for the size distribution in clouds. From just a very basic point of view, this is the same calculation. So the scalings here, they take into account merging, and this is where actually the expected iron droplet size, where both of these scalings come from actually, because the droplets merge, they will basically grow until the surface tension equals the kinetic stresses in the flow, and so the expected sizes are set by the competition of internal energy balance. So you want to grow to minimize your energy state, but at the same time, the shear stresses in the flow basically disrupt your droplets. So this is a characteristic size and not representative of there's a size distribution, absolutely. And also this is probably temporary. So this is not, so yes, droplets will eventually settle, but these scalings basically are approximately scalings for the equilibrium state that account for re-entrainment in the flow, settling behavior, and growth behavior.
Yeah, I see. Thank you. I just had a technical question on the Proteus framework. So that is so I recall the different components, modules that you are connecting. Do you envision this to be run on a large grid, or is this, how quickly is it run? Do you imagine running this on potentially on a planet population, or just sample parameter space on a few axes?
So in individual simulations with this specifically at the present point, and I want to point out, like these ones are in active development. So it depends on what you're specifically asking for. The general simulations don't take too long, maybe a few hours to at maximum a few days. But this is one simulation in one planet. So what I would do, or what I intend to do, is running a grid and then interpolating between different simulations, even though it is extremely sensitive to composition. And I think this is why we developed this model, because I think we have not grasped the complexity in composition space, what may happen. I think there are many different things to discover there, but I think it's doable. Yes. It's a question of what exactly, I think.
Okay, thank you.
Thank you. Do we have any more questions? Serena?
Thank you for the really interesting talk. I have a lot to digest, but I'd like to ask about the stellar properties, how sensitive those your model is based on the stellar properties like radiation, and for instance, if the parent star has a lot of variability due to, for instance, flares. Would that affect, how would that affect your result?
So the for these long, okay, so these are evolutionary calculations, and for the energy balance, it is really the integrated solar flux, meaning very small flares wouldn't make a difference. Now, assuming that this doesn't alter atmospheric composition dramatically. Now, I presume that very massive flares, like we start to see them for M dwarfs, specifically for active M dwarfs, I think can make a difference, specifically in the atmospheric composition. I don't know if I just simply don't know if they would alter magma ocean evolution as a global, in a global sense. I don't know. Something to be tested. Yeah. I want to argue though in that respect that the energy flux of the atmosphere is really set by more deeper layers of the atmosphere. So the photochemistry that is, for instance, induced by flares would really need to go very deep into the atmosphere and for a very long time to alter the heat flux properties of the atmosphere. So I'd say I would be skeptical a little bit about a very strong qualitative change due to flares on this evolution. But it certainly alters observable properties like upper atmosphere speciation and things like that. But we cannot compute it at the moment. So I think we need to test this.
Yeah, I was thinking about something like a coronal mass ejection level of a huge event, not the small flares.
Well, if it strips, it strips the atmosphere, then absolutely. The issue is if it's molten, then the planet can very rapidly actually re-equilibrate atmospheric mass levels. So if, for instance, you would strip the entire atmosphere, you actually outgas it very quickly because the mantle is at some extent is liquid, and that is really rapid. But in a partially molten regime, I don't know.
Thank you.
I don't know.
The answer.
So we got another question in the chat from Neil. Do you want to ask yourself?
Thanks. You talked mostly about interiors, but you did mention impacts. So I'm wondering if you could say just a little bit more about that connection. In particular, say you have, for example, a dry interior, and then you have later impactors. What are the issues that people might consider in how the structure of the planet might be altered by arrival of water at some later stage in its development?
Yeah. So, okay, two things. So first of all, these are extremely short period exoplanets. Sure, maybe they get a late veneer of water-rich materials. I don't know. If they would do that, let's assume there's a late veneer of water-rich materials and there's no water arrival or water inheritance by some other process prior to that stage, then I guess it depends on how much of that water makes it into the mantle. The models that we have there, basically, they don't know any about this, right? The yield stress or the lithospheric strength is an input parameter to the geodynamic model. And I'm just that these bullet points here are interpretations of what this may mean in that context. So if you're saying there is water on that planet, let's say on the night side where the temperatures are anyway very low, and it arrived very late, then indeed even volcanic emission on either hemisphere may fool us into thinking that the tectonics of the planet are indicative of the volatile accretion history. And maybe I should clarify this. Maybe this was part of your question. So water in principle, just as a very qualitative picture, is supposed to lubricate, let's say, subduction, because it basically lowers the melting point of rocks. That simplifies subduction events. So, or generally upper mantle mixing. And so, if there's water and if it's in the rocks, then this makes this easier. Rocks break easier. If there's no water, then it's harder and stiffer. Yeah. Did that answer your question? I'm not entirely sure.
Partly, yeah. Thank you.
Thank you.
Let us take one more question from Maxime.
Yeah, thanks. Hi, Tim. Hi, everyone. Very interesting talk. I was wondering one thing about the influence of hydrogen on the radiative flux that you showed, because as far as I remember, I might be wrong. Hydrogen doesn't have so much absorption, at least not as strong as water. And yet it seems, and that's what I guess you showed in your JGR paper, that hydrogen atmosphere do also have a strong, show a strong reduction in the OLR. So I was wondering whether that was due to line absorption or scattering.
No, it's because of collision-induced absorption. So above a specific pressure, I'm not sure what is the limit of, let's say, a few tens of bar. I'm not sure about the specific transition, actually. Basically, the molecules are so close together that they interact with each other, and the collisions between the molecules have different rotational frequencies, and that induces a greenhouse gas effect in a sense. So it's the collision-induced absorption of relatively high pressure hydrogen atmospheres that can induce greenhouse effect. It doesn't work for, let's say, 1 bar or something like this, or below. There's no greenhouse effect, but above a certain pressure range, there is.
Okay, I see. Thanks. Very interesting.
So there's one more question from Michael Way. If I may, I could read it for you. Excellent.
Yeah, I've read it.
Yeah.
No, please.
Yeah, you read it. Okay, Tim. Yeah.
So Michael asks about the effect of clouds. Everyone's favorite question, I believe. So a major problem with the Hamann and LeBron papers is a lack of clouds. And the Tobé paper recently that has tried to do that in 3D, but may not be the right clouds in the right atmosphere. Yeah, I don't know what am I supposed to do with this. Yeah. I think we can't do clouds properly in 1D, as you very well know. So what we will do, and we're currently working on this, is to implement various cloud schemes and just do parameter space exploration where we would model n-member cases of different cloud microphysics. I have tried to, I think the problem in general is a very degenerate problem, but this is partly on current non-ability of actually properly modeling the composition correctly over time, and partly that the problem is actually a degenerate problem. So my answer, I'm a theorist, my answer is a technical one. My answer is we should explore the theoretical parameter space as best as possible and find telltale signs of regime transitions and then probe them observationally. And if we find them, then this is good. And if we don't find them, or we find something other than we expected, then this is a sign that we have misunderstood something. So I have no solution for clouds. It would be great, but I don't. So we can only do trial and error, I think, at the moment. That is my answer to that question. Yeah, thank you.
Okay, let's all thank Tim again, and if we can unmute so we can applaud for the team.
Thank you everyone for your time.